When a high-voltage system fails, the resulting fault releases massive quantities of stored energy in a fraction of a second. The system must process that violent electrical spike, or risk catastrophic physical destruction. This is an actual oscillogram capturing the exact moment an energized transmission line is short-circuited. On the left, the initial impact registers as a chaotic, high-frequency spike called an impulse. Right after, the data reorganizes into smooth, low-frequency sine waves that slowly decay. The engineering problem is identifying the exact physical mechanism responsible for this transition. How does a localized, violent energy spike systematically transform into a uniform, cleanly dissipating standing wave? Mapping this transformation allows engineers to design power grids capable of absorbing faults without physical failure. To trace the mechanics of this energy transfer, we first have to examine the environment where it occurs, the compound circuit. This is any interconnected system composed of vastly different electrical properties, such as a high-tension transmission line connected to a step-up transformer. A massive power transformer stores a tremendous amount of energy in its magnetic field, but it possesses very low internal resistance. Left alone, it dissipates that stored energy slowly. We represent this temporal decay rate mathematically as the dissipation constant, denoted as U. For a transformer, U is a very low number. By contrast, a transmission line possesses a high dissipation constant. It burns off stored energy rapidly through its resistance over miles of copper. This creates a strict physical mismatch. If you were to completely disconnect the two, the transmission line's transient energy would die out in milliseconds, while the transformers would linger for several seconds. But they operate as a single compound circuit. Because they are wired together, their transient oscillations are forced to die down simultaneously. To prevent a violation of the conservation of energy, the system has to balance itself out. The transformer must actively dump its excess stored energy into the transmission line. This mandatory geographical movement of active power between sections is the physical origin of the traveling wave. A stationary wave simply oscillates in place. The traveling wave actually moves distance over time to bridge the gap between mismatched components. The traveling wave provides the necessary mechanism for this active power transfer, stabilizing the mismatched components of the circuit. The physical behavior of any wave is entirely dictated by the phase relationship between its current and its voltage. In a stationary wave, current and voltage are 90 degrees out of phase, an alignment known as quadrature. Because we peak at different times, multiplying them yields zero average power. Power simply surges locally without moving down the line. This behavior is the transient equivalent of reactive power in a permanent alternating current circuit. Shift focus to the traveling wave. Here, current and voltage align, so their peaks and zero crossings are perfectly in phase. Multiplying them forces the resulting power wave entirely above the zero line, guaranteeing a steady, continuous flow of effective power in one direction. This in-phase alignment is the transient equivalent of active, real power transfer. Transient waves cannot simply be algebraically combined the way we mix effective and reactive loads in standard AC circuits. The traveling wave possesses a spatial progression factor that the stationary wave lacks entirely. As a traveling wave physically moves down a line, its power intensity continually decreases over time due to the dissipation constant, U. But temporal decay is not the only variable. The wave also interacts geographically with the physical copper line elements it passes over. This requires a spatial counterpart to the dissipation constant, the power transfer constant, denoted as S. This chart maps spatial decay. When the power transfer constant is zero, we see uniform power flow. Energy drops strictly according to baseline dissipation. If the constant is negative, power drops off much more sharply, decreasing spatially faster than baseline. In this negative state, the wave leaves energy behind, supplying power to line elements and slowing overall temporal decay. Conversely, a positive constant means power flow decreases much slower than baseline, extending further along the wire. In this positive state, the wave is actively draining stored energy out of the line elements as it passes, effectively accelerating the system's temporal decay. These spatial and temporal decrements function simultaneously. They combine into a single complex exponent that precisely maps the wave's entire physical lifespan. This makes the traveling wave a dynamic thermodynamic engine, negotiating its energy exchange with the physical copper at every millimeter of its journey. Real-world events like a lightning strike or a heavy switched load force massive quantities of energy into a localized part of the circuit. This creates an impulse, which is physically just a traveling wave of effective power, characterized by an extremely steep wavefront. This steep-fronted impulse races violently down the transmission line, carrying the initial chaotic electrical spike forward with it. This fast-moving energy will inevitably hit a terminal boundary, such as an open circuit, a physical switch, or a heavy transformer. The survival of the grid depends entirely on the rigorous wave mechanics that dictate what happens in the microsecond that impulse hits the physical boundary. When the traveling impulse strikes the boundary of the line, it cannot proceed. The energy is forced to reflect backward along the exact same path. As the incident wave moves forward into the boundary, it instantly generates an inverted secondary wave moving in reverse. Occupying the exact same physical space, they overlap to form a single combined waveform undulating strictly up and down. This is superposition. Because the reflected wave travels in the opposite direction, its spatial coefficient s carries the opposite mathematical sign. When added together during superposition, they negate each other's directional progression. Through reflection and superposition, the destructive travel-in wave of effective power is instantly converted into a stationary wave of reactive power. Returning to our original empirical data, we can map this theoretical process directly to reality. The chaotic data on the left is the raw impulse arriving and reflecting. The uniform data on the right is the physical proof of superposition. The energy is now safely trapped in a stationary wave, quietly bleeding off its intensity. In a fraction of a second, the phase angle between the current and the voltage has definitively shifted from entirely in phase to perfectly in quadrature. By mastering the variables of dissipation and power transfer, engineers deliberately harness this mathematical transformation. They build grids that force deadly, chaotic electrical impulses to restructure themselves into harmless standing waves that safely dissipate into the air.